let's take a look at simulation. Like I said, I think that it's a good idea to start out with just talking about simulation, and then next week, if you all bring your laptops in, we can do a little bit of Visual Basic. I tried this for the first time last year, and the class seemed to like it, because I think that Visual Basic in Excel is very, very handy to use. It's a good tool. And that way you get some basic understanding of it. And there's tons of videos on YouTube for learning Visual Basic. It's really quite good. It's a bunch of good ones that I ran across. So I'll get you started. This one I put in because I thought it was fun. This was something that back in the 80s was considered the ultimate on computer programming. It's probably way outdated now, but basics of computer programming, you probably still find it in there. The rest of them are things that I drew on to write the lecture. Okay. The idea of simulation, I mean, everybody has an intuitive idea of what simulation is. But computer simulation is to allow you to model systems that are primarily ones that are not conducive to analytical analyses. You're essentially doing an experiment with it that you can repeat thousands or hundreds of thousands of times, because it will do it over and over and over as often as you want, and then you can collect statistics on the behavior of it. What limits it is how well you understand, for the most part, how well you understand the system and the distributions of the events in the system. So what we do, what I'm going to show you is a barbershop simulation, because that's very typical. You know, in operations research, there's a whole branch of queuing theory. I don't know, have you guys heard of that? Queuing theory, and all it is a study of lines. I mean, that sounds really dull, but there's a lot of companies that are very interested in the way lines and queuing behaves.
Yeah, so this would be like similar to like the boarding order when you get on a plane, like how to board a plane most efficiently and stuff like that.
You could probably model that, yeah.
Because I know people have done that. I don't know if they use this method.
Well, simulation is generic. There's a lot of different tools out there. But one that is probably the most common is it's called microsync. And I believe they use that for something like that. It's a system analysis and integration, or something like that is what that stands for. But it's a simulation system. The most common, the one that when I had a course in simulation, and the one that we used, which is supposed to incorporate the elements of just about every system you'll encounter, is called the African tanker problem. Why it's a tanker and why it's in Africa, I don't know, but that's what it's called, African tanker. Because what you have is tankers coming to port, and then you have tugboats going out, and so they queue up out in the harbor, and then they have tugboats that come out and pick up each of the tankers, and they escort them into their berth, and then they have an unloading time, then they have to deberth them with the tugboats, and then they take off. And then you can have storms that stop all the operations and allows the queue to build up out in the harbor. And then you assume distributions for each one of those events. That's called a time-driven simulation, because it's based on the current time. You have to have an internal clock built into your simulation. And that's why this barbershop example is one where you might have to have an internal clock built in. And here you'd have a simulation where you'll have arrival of the next customer. Well, that's probably, inter-arrival times are usually exponentially distributed. That's what data show. And then you have to determine whether or not your barber is currently serving another customer, currently cutting somebody else's hair or whatever. If they are idle, then you can make the server busy. You have to set them to being busy, and then you schedule the customer departure. Could be rival, could be something else, doesn't matter. And then when after they're done, then you set the server to idle. If the server is currently set to idle, then you would say that if the server is idle, if the server is not idle, certainly currently serving another customer, then you have to build up your queue. And that's probably what's of most interest to most people, is how many customers are in the queue, or how many items are in the queue, whatever it is. And then they have to wait until the server is idle for their turn, and then you take them out of the queue, set the server to idle, or set the server to busy, and then schedule their departure. And when they depart, you have to go back to the queue. Queue's empty, then you have an idle server doing nothing, which is another thing you probably want to keep statistics on. How often is this guy not doing anything, or this part in the system? So you would collect statistics on the average time of service, the average time of waiting. If there's any idle time where they're not doing anything, or they're not immediately picking up another customer, you would want to determine that. You'd want to schedule the number of arrivals, determine the statistics on the number of arrivals. There's all sorts of things that you can get out of a simulation like that. And in order to do that, you have to program distributions into the system. You have to program a timer into the system, and you also have to program a means for keeping statistics. And so I could say I want to see what happens. Say this operates for an 8-hour day. And I want to see what happens in the course of 1,000 8-hour days. And then you get statistics by day and overall. That you can group them any way you want to. And that you can do almost instantaneously. When I was taking this, we had I probably shouldn't admit this, but we had to program on backs. And you had to schedule your time to use it, because other people were programming stuff too. But even that ran fairly quickly. But now they're almost instantaneous. And when you run a simulation, it doesn't take any time at all. So there's two types of simulations. The one with the African tanker or barber or whatever type of queuing system are called event or time driven. In other words, as you move through your clock, you find out what the server's doing. You can find out how many people are in the queue, or items are in the queue, how long their average wait time is, that sort of thing. If time isn't an explicit element, it's called a Monte Carlo simulation, for obvious reasons. Maybe now we should start calling it a Las Vegas simulation, I don't know. But at the time it was named, it was called the Monte Carlo simulation. So one of the most important things of these simulations is randomness. And we have to drive this by true randomness. And in time-driven models, the inter-arrival times, service times are all based on a random number. And time to failures might be in a Monte Carlo simulation. So we have the problem associated with generating random numbers. Almost always we're interested in random numbers uniformly distributed between 0 and 1. And that's the standard for random number generation. And what we call them is U sub I. That's our random number. And we expect them to be distributed uniformly between 0 and 1. When you think about it, if you're using an algorithm, which a computer has to do, it's not truly random. Because it's algorithmic. It can be repeated, so it's not random. So you have to put a little thought into generating your random number so that it at least appears random. But so that you can also replicate it if you need to. These are experiments, so you have to be able to replicate them. And unless you can replicate your random number stream, which is pseudo-random now, because we never have a truly random number stream. Okay? With our pseudo-random number stream, we have to be able to replicate it. Okay, so there was a time when actually, the Rand Corporation at one time came up with a device that's all it did. It was capable of doing, was generating random numbers. Sometimes they'll calculate pi and use sets of 4 digits from pi out to as many decimal places as possible for the random numbers, because it's an irrational number. There was, let's see, what's another one that I read one time? Oh, one time I read that what they did was set up a plate for detecting gamma particles. And during every time interval, they just counted the number of gamma particles that were hitting this plate. And that was a random number generator. That's as close as you can get. I mean, they went to a lot of interesting means to get random numbers in order to do simulations. But now, like I said, we can do it, but we have to trick our simulations in such a way that these pseudo-random numbers that we generate at least appear random. And for them to appear random, they have to appear uniformly distributed. And that's the first requirement, is that they have to be uniformly distributed. And the second requirement is that they have to be what's called identically distributed. That should be distributed. Okay. So these, there's a number of algorithms. The one that I'm going to talk about, and I don't want to go into it a lot. And oh, by the way, there is a function in Excel that generates random numbers between 0 and 1. It's random and empty parentheses. You can put a seed in it. There's a number of things you can do. But rand, that's what I use to assign lab groups in class, and I use it to assign order of presentations and that sort of thing. I always use the Excel random number generator. It's very handy, for me at least. But there is, and I wanted to go into it a little bit, one of a number of algorithms. It's called linear congruential generator, an LCG, that's been shown to generate uniformly distributed random numbers. And first of all, before we go any further, has anybody heard of a modulus function? Or a div function?
Div.
I'm sorry?
I've heard of div.
Div, okay. Well, div returns, and these are like programming terms. Div returns, for instance, 10 div 3 returns 3, because 3 goes into 10 3 times, and without the remainder. Whereas 10 mod 3 returns 1, because that's the remainder of that division. So the modulus, or mod, function returns the remainder. The div function returns the integral division. Okay? So they're kind of the complement of each other. And that's what this is. This is the modulus function. It returns the remainder. For the linear congruential random number generator, you have the multiplier, and we'll talk about the requirements for that. The seed, the z sub 0 is called the seed, the starting value, and there are criteria for assigning the seed value. And the seed, because it starts it's what generates all the rest of the random numbers. C is the increment, and there are multiplicative and mixed linear congruential generators. And this is that increment, this guy right here, is 0 for multiplicative and greater than 0 for mixed. We'll do mixed just to mix it up. Pun intended, sorry. I couldn't resist it. And then m is the modulus. I'm sorry, the modulus is the number of the function is modulo. I'm sorry about that. That's the remainder of the division. The requirements is that the modulus has to be greater than 0. It has to be greater than a multiplier. It has to be greater than the increment, and it also has to be greater than the seed. You also have to have a modulus that is large enough that you don't cycle through. your random numbers in a short period of time. So generally, and I need to look this up, how to do this in Excel, but usually you choose whatever the maximum integer is that's available on the computer. Okay, a lot of times when you're programming, there's always a name for that. On a VAX, for instance, it was called maxint. It was the largest integer available that it could generate. I just use a very large number, usually up to at least to the 18th to the 27th power type number. It has to be very large, and Excel can handle that. So you choose a modulus that's really large, and then you just, with your multiplier and your increment, as long as they're less than your modulus, you're okay. So like I said, I use 10 to the 9th. I usually actually go larger than 10 to the 9th for the modulus. And this is just an example of one of the requirements is A mod 4 for if A is 1, A mod 4 is 1, is 5 is 1, and 9 is 1, and so on. So 14 mod 4, that's 2, yeah, I made a mistake there. I think I meant to write 13. Yeah. So A mod 4 is, that should be 13, that's a mistake. Okay. So one thing you have to note is that the common denominator between C and the modulus has to be 1. And A mod 4 should equal 1 also. Number of requirements for each of the variables, but this is what happens when you have a small modulus. Let's say that the modulus is 16. And if the modulus is 16, these are our increments. So 0 is for, this is z sub 0. That means that our seed is 7. And that's not a very good seed either, it's too small. But the seed is 7. Right? So that's z sub 0. And then on the first increment, that becomes 6, because it's 5 times, we'll write this down. So for 0, for the first increment, it would be the z sub 1 would equal 5 times z sub I minus 1, which in this case is 7, plus 3. Okay, 5 times 7 plus 3, that is 38, right? So 38. And then you do mod 16. Okay. Mod 16 is 32, so that's 6, right? Because 16 goes into 32, and then there's 6 left over. So that means that the z sub 1, that's where the 6 comes from. Then the random number that's generated from that is the z sub I divided by 16, because that's our modulus, because you use the modulus twice. And that modulus is then u sub 1 is equal to 6 over 16, and that's where we get a 0.375. Okay. And the u sub I is our random numbers between 0 and 1. But with a modulus of 16, look what happens after the 16th repetition. 17, it starts to cycle. 375, 0.063, and 5. And that's the reason for using a very large modulus, because if you have a modulus of a quintillion, you can do a lot of experiments before you're going to ever cycle your random number generator. And that's the idea.
Just, can you go back one slide?
Sure.
In your example, your z sub I on the board. So you're going, your I is 0 in that example?
In this example, I is 1. Because
okay.
z sub 0 is always the C. Z sub
Right.
0 equals 7.
So if your I is 1, I 1 minus 1 is 0, and that's where you get your 7 on the board, 5 times 7.
Yes.
Okay.
Yeah, exactly. Because this is my A. This is Z, I minus 1.
Okay.
This is C. Yeah. And this is my modulus.
Okay, thanks.
Okay. So you can do either an empirical test, do a random number generator, where you actually go ahead and generate random numbers and do a test on them, or a series of tests. Or you can do it mathematically. I think for our purposes, it's going to be more interesting to do it empirically. And so that means that they have to be, we have to test to see whether they're identically and uniformly distributed. Like I said, this is uniform distribution between 0 and 1. This is identically and independently distributed. I think I forgot to say independently. That's what ID stands for. So the test for uniformity is a chi-squared test. So you take your random numbers and you divide them into k subintervals between 0 and 1. And they have to be, there has to be at least 100 subintervals. Since our random numbers are between 0 and 1, that means that the first subinterval is going to be 0, greater than or equal to 0, and let's see, what do I call it, k sub I. So k sub 1 would be greater than or equal to 0 and less than 0.01. And 2 would be greater than or equal to 0.0. 0 is less than or equal to. So 0.01 is less than or equal to, 2 is less than 0.02. You keep going like that until you get 100 subintervals. So that's your 100 subintervals that you're going to count the number of random numbers that fit into each one of those subintervals. And then you take your uniform, the number that you've generated, and it has to be at least 100, but it actually has to be at least 500 because n over k has to be at least 5. And so that means you have to generate at least 500. So n has to be at least 500. And then f sub j is the number of random numbers in each one of those subintervals. And then what you test it for is with k minus 1, 1 minus alpha degrees of freedom, because we want to do a one-sided test. This is a test that you don't want to reject the null hypothesis. You reject the null hypothesis, that means that these are non-uniform and you can't use them. They're not valid random numbers. So I call these bins, these intervals. So this is the first bin, less than 0.01. This is a set of greater than or equal to 0, less than 0.01, greater than or equal to 0.01, less than 0.02. And this is the frequency in each one of those intervals, all the way up to the 100th interval. And this is the number of random numbers that have occurred in each one of those subintervals. And then that's just the intermediate value for this calculation. The frequency times minus n over k quantity squared for each one of the intervals. So you end up summing that. That's this operation right here. And then you multiply it by the number of subintervals, which is 100 over n, which is the total number of random numbers you've generated, and you get your chi-squared value. In this case, it's 112.8, and chi-squared with 99 degrees of freedom, which remember is our 100 subintervals minus 1, at 0.95, 1 minus alpha, which is 123.55. So that means that these are, we can't reject the null hypothesis that they are uniform. that there's no substantial variability, non-uniformity along the entire subintervals. And that's good, because we don't want to reject the null hypothesis in this case. So, my generated random numbers are uniformly distributed, and they met the first criteria. The last test that we talked about was for uniformity. The other requirement of our random number string is that it be independent and identically distributed. What this means, practically, is that you don't want too many numbers that are consistently increasing from the previous one. So, for instance, 1, 2, 3, 4, 5, 6, and 7. That's an increasing run of 6, because that's a run of 7, I mean, because that's a run of 1, 2, 3, 4, 5, 6, and 7. So that's a run up, in this case, equal to 7. And likewise, if I had, you know, 11, 10, 9, 8, 7, 6, 5, 4, that would be a run down of 1, 2, 3, 4, 5, 6, 7, 8. Okay. I don't want long run-ups or long run-downs, because that violates the independence and identification, and identically and independently distributed assumption. So, what you need to do, and this is why we use a program, is to count the number of runs. And we're only interested in runs up in this particular algorithm, as runs up. We could also do it for runs down, but it doesn't matter. We're only interested in runs up. Okay, so here we have 10 random numbers generated. And what we're interested in doing from that is to find the number of runs of length 1, runs of length 2, runs of length 3, runs of length 4, runs of length 5, and runs of length 6 or more. And that's what this matrix means. Now, this is a run of 1, because the next number is less. This is a run of 2, because this one's higher than this one. This is a run of 2. This is a run of 3. This is a run, actually this is a run of 4, sorry. And this is a run of 1. Okay. So I have 2 runs of 1, 2 runs of 2, 0 runs of 3, 1 run of 4, 0 runs of 5, and 0 runs of 6 or more. That's the way you count it. You can't do 500 or more random numbers like that. That's not possible to do. Well, it might be possible, but nobody wants to do that. So, but you have to develop from your stream of random numbers a count in this format, in this matrix of a 6x1 matrix. What you do with that, then, is that's one of your variables. This, believe it or not, this A sub ij is a matrix of constants. Okay, those are constant. The B sub i's are a matrix of constants. These were developed by non-parametric statisticians. I don't think I need to say any more. The only ones that could develop a 6x6 matrix of 5-digit numbers to use as constants. And these are constants. What's going to change is our R matrix, because the R matrix changes according to your, so this is variable according to your random number string. Okay. Now I had a run of random numbers of 500, and this was my runs matrix, my R matrix. That's what it came out to. Okay. What we want, if we want it to be independent and identically distributed, we want it to cluster down here and peter out as it gets to the higher ones. That did that. That's good. Okay. That satisfies that requirement. Now we test it. And the test statistic, which is chi-square distributed, is this. Let's think about what that does. So for I is one, I have one. First of all, this is 6 times 6. This is 36 operations. Okay? So you set this one equal to 1, and then you run through 1, 2, 3, 4, 5, 6, and you set this equal to 2, and run 1, 2, 3, 4, 5, 6. 36 different operations. The subscript directs you to the contents of this matrix. So Aij, let's say that I is equal, just arbitrarily, I is equal to 2 and j is equal to 4. That means that it's row 2, column 4, and this is my Aij, 36,187. Row R sub I means that it's 2, n is constant, b sub I is 2, and j is 4, and b sub j is 4. So that means in this case, I would go to R sub I, which is R2, which, let's say we're doing this one, that would be -2, minus n, which in this case is 500, times b sub I, b2, 524, times R sub 4, which is 19, minus 500 times b sub 4, which is this right here, 19 over 720. Okay. And this is n, you can wait until the end, that's about 500.
And your A sub ij in the test statistic formula is?
36,187.
Oh, okay, great.
So it's row 2, row 2, column 4. Now, let me go a couple more slides and then let's take a look at the program. So I take my critical value. It has 6 degrees of freedom. 1 minus alpha, that's my chi-squared. So if n is 10, that means that this is, my R is 3.134, which I calculated from the data on the previous slide. And that's less than our critical value of 12.592, interestingly enough. And that means that these are independently and identically distributed. My 10 random numbers, as well as my 500, which ended up being 8.284, which is still less than that. I couldn't reject my null hypothesis. And when you don't reject the null hypothesis, your conclusion is that they're independent and identically distributed. Like I said, with both of these, we don't want to reject the null hypothesis, or else they're not uniform or not independent and identically distributed.